We stand on a tiny world gazing into an endless ocean of stars, yet we understand almost none of it. The universe is filled with profound mysteries that defy our best science and haunt the dreams of the greatest thinkers. Today, we are embarking on a journey to the very edge of human knowledge to confront the 30 most baffling cosmic questions we still cannot answer. By the end, you will see the cosmos not as a static backdrop, but as a living puzzle of incredible depth and wonder. We will grapple with invisible forces shaping reality and confront the possibility that time itself may have a beginning. What single cosmic mystery keeps you awake at night? Our journey begins with a ghost, not the kind from stories, but a cosmic specter so pervasive that it outnumbers the atoms you and I are made of by a factor of 5 to 1. This is the first and perhaps greatest of our cosmic puzzles. What is dark matter? For nearly a century, astronomers have known something was terribly wrong with the way the universe moves. Look at a galaxy like our own Milky Way. All those stars are orbiting the galactic center, held in place by the immense gravitational pull of all the other stars and gas in the galaxy. But when scientists calculated that pull based on everything they could see, the numbers did not add up. The outer stars were moving far, far too fast. According to the visible mass alone, those speeding stars should have been flung out into the intergalactic void long ago, like marbles launched from a broken slingshot. Yet the galaxies hold together, something invisible, something that exerts gravity but gives off no light whatsoever, must be holding them in its grip. We call that something dark matter. Think of it like this: you are watching a merry-go-round in a park at night. You can see the children laughing and spinning under the lights. But the merry-go-round is spinning much faster than the visible children could possibly make it move. Your only conclusion is that there are many more invisible children hanging on in the darkness, their weight causing the furious spin. In the cosmos, dark matter is those invisible children. It does not emit, absorb, or reflect a single photon of light. It is utterly transparent to the entire electromagnetic spectrum. We cannot see it with any telescope ever built. We only know it's there because of the gravitational handshake it shares with the things we can see. It tugs on stars, it bends the light from distant galaxies, and it forms the invisible scaffolding upon which the entire visible universe is built. So what could this mysterious substance possibly be? The leading idea points to a new, undiscovered class of particle. One candidate is known as a WIMP, which stands for Weakly Interacting Massive Particle. As the name suggests, these hypothetical particles would have mass and interact only through gravity and perhaps the weak nuclear force, making them incredibly difficult to detect. Another intriguing candidate is the Action, a theoretical particle originally conceived to solve a different problem in particle physics. It would be astonishingly light, potentially streaming through the universe in vast, wave-like clouds. The hunt for these phantoms is one of science's grandest endeavors. Deep underground, in mines and tunnels shielded from cosmic rays, scientists have built ultra-sensitive detectors. They wait in profound silence, hoping that just once, a dark matter particle will whisper its existence by bumping into the nucleus of an atom in their apparatus. So far, the detectors have heard nothing but silence. This ghost holding the galaxies together remains utterly elusive. It is the universe's most dominant material, and we have no idea what it is. But if dark matter is the ghostly glue holding the cosmos together, then its counterpart is a phantom force tearing it apart. Our second great cosmic question asks, what is dark energy? While dark matter pulls with an invisible gravitational hand, dark energy pushes. It is the mysterious pressure causing the expansion of the universe to accelerate, not slow down as everyone expected. This discovery in the late 1990s was so shocking it upended cosmology and earned its discoverers the Nobel Prize. How did they find it? By staring at the death throes of stars in galaxies impossibly far away. Astronomers used a specific type of exploding star, a supernova, as a cosmic mile marker. They knew how bright these stellar explosions should be, so by measuring how dim they appeared from Earth, they could calculate their distance. But they also measured how fast those galaxies were moving away from us by the reddening of their light, a phenomenon called redshift. The expectation was simple. The gravitational pull of all the matter in the universe, both seen and unseen, should be acting like a brake on the expansion from the Big Bang. The more distant supernova should show that this cosmic braking was in effect. The data told a different story entirely. The most distant, ancient explosions were fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible explanation was that the expansion of space itself had been slower in the past and was now speeding up. Some repulsive force was overwhelming gravity on the larger scales, pushing galaxies apart from one another at an ever-increasing rate. The leading candidate for this force is as strange as it gets. It may be a property of empty space itself. In Einstein's equations of general relativity, there is a term called the cosmological constant, which he originally inserted to keep the universe static. He later called it his greatest blunder when the universe was found to be expanding. But now it seems he may have been right for the wrong reason. This constant represents a baseline energy density inherent to the vacuum of space. Even in a perfect, empty void, according to quantum physics, virtual particles flicker in and out of existence. This quantum foam should imbue every cubic centimeter of nothingness with a tiny amount of energy. This vacuum energy could be the dark energy that drives the acceleration. Here lies the problem, and it is a spectacular one. When physicists calculate how much energy this quantum vacuum should have based on known theories, the number is absurdly, catastrophically wrong. It is off by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is the worst theoretical prediction in the history of science. This monumental failure is known as the vacuum catastrophe. It means our understanding of the quantum world and the large-scale structure of the universe are fundamentally at odds. Dark energy, making up about 70% of the universe's total energy budget, remains a label for our ignorance. Is it truly the cosmological constant, or something more dynamic and strange that evolves over time? We watch the galaxies flee from each other into a lonely, dark future, driven by a force we cannot see or comprehend. Dark energy's acceleration forces us to look backward to the very beginning of everything. This leads us to our third great question, one that may be the ultimate limit of human inquiry. What happened before the Big Bang? The standard story of the Big Bang is powerful and elegant. It tells us that about 13.8 billion years ago, the entire observable universe was compressed into an unimaginably hot, dense, singular point. Then it began to expand and cool. From that primordial fireball, particles formed, then atoms, then eventually stars and galaxies. But crucially, the Big Bang theory describes the evolution of the universe from that hot, dense state forward. It says nothing about where that initial state came from, or what, if anything, preceded it. The equations of general relativity simply break down at that point of infinite density, a moment scientists call the singularity. It is as if you found a fascinating, detailed biography of a person that started abruptly with them as a fully grown adult. You are left desperately wondering about their childhood, their birth, their very origin. So, did time itself have a beginning? If the Big Bang marked the creation of space and time, then the concept of a before becomes meaningless, like asking what is north of the North Pole. This is a profound philosophical cliff edge, yet many physicists are not satisfied with that as a final answer. They have proposed breathtaking ideas that stretch our understanding of reality itself. One leading theory is cosmic inflation. This suggests that a fraction of a second after the initial moment, the universe underwent a period of exponentially faster than light expansion, smoothing it out and planting the seeds for galaxies. Some versions of inflation are eternal, suggesting our Big Bang was just one bubble in a frothing, endless multiverse of other expanding bubbles, each with its own laws of physics. In this view, there was no single beginning but an endless cycle of creation. Another mind-bending idea is the Big Bounce, a cyclical model where our expanding universe is the result of a previous universe collapsing in a big crunch, then rebounding. Time and space would then be eternal, cycling through phases of expansion and contraction. Perhaps the most poetic is Sir Roger Penrose's conformal cyclic cosmology. It proposes that in the far, far future, when the universe has expanded into a cold, empty sea of radiation, the distinction between particles and photons blurs. This endless, featureless state can be mathematically linked back to the hot, dense, featureless state of the Big Bang. In this view, the end of one universe becomes the beginning of the next in an infinite, timeless loop. Each of these theories tries to peer beyond the veil of the singularity. They are not just wild speculation, but frameworks built from the mathematics of general relativity and quantum mechanics. Yet they remain untested, sitting just beyond the reach of our current observations, so we are left at the precipice, staring into the abyss of our own origin. Was there a true beginning, a first moment when time flickered into existence, or are we living in just one chapter of an infinite cosmic story, with no first page and no final chapter? The silence before the bang is the loudest question we can ask. The silence of our cosmic origins is mirrored by another, more pressing quiet all around us. If the universe is so vast and ancient, brimming with hundreds of billions of galaxies, each with hundreds of billions of stars, then where is everybody? This is the heart of our fourth great question, a puzzle so famous it has a name, the Fermi paradox. The physicist Enrico Fermi posed it bluntly over lunch one day in 1950. Given the sheer scale and age of the cosmos, there has been more than enough time for other intelligent civilizations to arise, spread, and make their presence known across the galaxy. Yet we see no signs of them, no grand constructions, no visiting ships, not a single whisper on the cosmic radio. The sky, for all its splendor, is profoundly silent. To frame this mystery, scientists use a powerful tool called the Drake equation. It is not a strict formula with one answer, but a way to organize our thinking. It multiplies a series of probabilities, starting with the rate of star formation in our galaxy and moving through the fraction of stars with planets, the number of those planets that could support life, the fraction where life actually emerges, the fraction where that life becomes intelligent, the fraction that develops technology to communicate across space, and finally, the length of time. Such a civilization lasts, plug in optimistic numbers, and the galaxy could be buzzing with conversation. Use more conservative estimates, and we might be utterly alone. The equation lays bare every step where our ignorance resides. The staggering gap between that high potential for life and the eerie silence we observe leads to possible solutions, each more unsettling than the last. One dominant idea is the Great Filter. This theory suggests that somewhere in the progression from sterile matter to a spacefaring civilization, there is a step or a barrier that is almost impossible to pass. It could lie in our past, perhaps the miraculous jump from non-living chemistry to the first self-replicating cell. If that step is extraordinarily rare, then the filter is behind us and we are among the first lucky ones. The more terrifying possibility is that the Great Filter awaits us in our future. Perhaps every advanced civilization reaches a point of technological development where it inevitably destroys itself through climate catastrophe, nuclear war, or some technology we have not yet conceived. The silence, then, would be a cemetery quiet. Other solutions are less dire but equally strange. The zoo hypothesis proposes that advanced civilizations are out there and aware of us, but they have chosen to observe us from a distance, following a strict non-interference policy, leaving our world as a cosmic wildlife preserve. Another possibility is that we are simply too early or too late in the cosmic timeline, missing the grand conversation by billions of years. Or perhaps the answer is simpler, and technological intelligence like ours is a bizarre fluke, a one-in-a-trillion accident of evolution where the advantages of tool use and abstract thought are not the inevitable pinnacle of life, but a rare and fleeting curiosity. Despite the silence, the search is more active than ever. For decades, projects like SETI, the search for extraterrestrial intelligence, have scanned the heavens with radio telescopes, listening for a patterned signal that shouts, "We are here." Newer efforts look for laser pulses or other techno-signatures, and the search is broadening beyond intelligence. Upcoming missions to the icy moons of Jupiter and Saturn, like Europa and Enceladus, will probe their hidden oceans for any sign of microbial life. The discovery of even simple, single-celled organisms on another world would be revolutionary. It would tell us that the step from chemistry to biology is not a miracle, but a common cosmic process. If life can spark twice in our own solar system, then the universe is likely a garden teeming with living worlds. The silence of intelligence would then become an even deeper, more haunting mystery, pointing us back to that daunting possibility of a great filter still ahead. We are left listening, wondering if the next great discovery will be a faint signal in the static, or the crushing realization that in all this immensity, we are the only ones asking the question. The profound silence of the cosmos forces us to look not only outward but forward to a horizon so distant it defies human comprehension. Our fifth great question asks, what is the ultimate fate of the universe? The answer depends entirely on a cosmic tug-of-war, a battle between the relentless pull of gravity and the mysterious push of dark energy. Based on our best measurements today, we can project three possible endings, each more dramatic than the last. The first and currently most likely scenario is known as the Big Freeze or heat death. In this future, dark energy continues to dominate, accelerating the expansion of space forever. Over trillions upon trillions of years, galaxies will recede from each other until they vanish over our observational horizon. Star formation will cease as interstellar gas is used up or flung apart. Existing stars will burn out one by one, leaving behind cold remnants, black dwarfs, neutron stars, and black holes. Even these titans are not eternal. Over timescales so vast they make the current age of the universe seem like a single heartbeat. Black holes themselves will slowly evaporate through a process called Hawking radiation. What remains is a universe that is cold, dark, and almost perfectly empty, a thin soup of fundamental particles and photons stretched so far apart they almost never interact. It is a quiet, eternal fade to black, the ultimate triumph of entropy where no energy can ever be harnessed to do work again. The second, more violent possibility is the Big Rip. This occurs if dark energy is not constant but grows stronger over time. Imagine that repulsive force increasing until it overwhelms not just the gravity between galaxies, but the forces holding galaxies, stars, and even atoms themselves together. In a final, catastrophic moment, the fabric of space would expand so violently that it would tear apart galaxy clusters, then galaxies, then solar systems. Stars would be shredded, planets ripped from their orbits, and finally, molecules, atoms, and even atomic nuclei would be pulled apart into their constituent particles. The universe would end not with a whimper, but with a definitive, terrifying tear in reality itself. The third classic scenario is the Big Crunch, a dramatic reversal of our current expansion. This would happen if the density of matter and energy in the universe were high enough for gravity to eventually win the battle. After many billions of years of expansion, the universe would slow, halt, and begin to collapse back in on itself. Galaxies would rush together in a blue shifted blaze, temperatures would soar, and all structure would be compressed back into a hot, dense state, perhaps triggering a new Big Bang and another cycle of existence. This cyclical model is poetic, but current data strongly disfavors it. Our observations of distant supernova and the cosmic microwave background radiation consistently point to an accelerating expansion, making the cold, lonely Big Freeze the leading forecast. Yet, even this is not the final word on cosmic endings. More speculative ideas lurk in the far future. One is vacuum decay. This stems from the idea that our universe may not be in the true, most stable state of empty space, but in a false vacuum, a kind of cosmic valley that seems stable but isn't the absolute lowest energy state. A random quantum event somewhere at some time could create a bubble of true vacuum. This bubble would expand at the speed of light, rewriting the fundamental laws of physics as it goes. The wall of this bubble would be an annihilating wave of new reality, destroying everything in its path without warning. It is a sobering thought that the laws we rely on might be temporary, and the universe could change its rules in an instant. Another distant possibility is that in a universe trillions of years old, a random quantum fluctuation in the vast, empty void could spontaneously spawn a new Big Bang, igniting a fresh universe in the ashes of our old one. These are not science fiction, but logical extrapolations from our most fundamental theories of quantum mechanics and cosmology. They paint a picture of a cosmos with multiple possible endings, from a slow freeze to a sudden rewrite. Our fate, written in the invisible ink of dark energy, is still being decoded. The ultimate fate of the universe is written in the shadow of its most perfect destroyers. Our sixth question takes us to the edge of the impossible, to a place where gravity wins its final, absolute victory. What is inside a black hole? We can describe the journey to one, but the destination remains the greatest mystery in physics. Picture a star many times more massive than our Sun collapsing under its own weight after its fuel is spent. The core crushes down, and if it is heavy enough, no known force in the universe can stop it. The collapse continues until the matter is compressed into a point of zero volume and infinite density. This is the singularity, the heart of the black hole, where the mathematics of Einstein's general relativity simply shatter. Space and time, as we understand them, cease to exist. The laws of physics, our guide to the cosmos, break down completely, but you cannot see the singularity. It is hidden behind a one-way membrane called the event horizon. This is the point of no return. Think of it as a cosmic waterfall. If you are floating in a river far from the falls, you can paddle against the current and escape. But once you cross the lip of the waterfall, no amount of paddling, not even with the power of a rocket, can bring you back up. The current of space-time itself becomes inescapable. For a black hole, that current is gravity. Cross the event horizon, and all paths through the fabric of space-time lead inward toward the singularity. From the outside, we would see you slow down, redden, and fade from view as the intense gravity stretches the light you emit. But for you, assuming you survived the tidal forces, crossing the horizon might be uneventful. You would not see a shimmering wall or a cosmic sign. You would simply be on a journey to an end from which there is no return, a journey where the future itself is a location, the singularity. This leads to a paradox that has divided physicists for decades. It is called the black hole information paradox. According to quantum mechanics, information is never truly lost. If you burn a book, the ashes and smoke still contain, in principle, all the information needed to reconstruct every word. The information is scrambled, but it is preserved in the particles. Now, what happens if you throw that book into a black hole? Stephen Hawking showed that black holes are not completely black. Due to quantum effects at the event horizon, they slowly evaporate, emitting a faint glow we now call Hawking radiation. This radiation is thermal, meaning it is random and featureless, carrying no information about what fell in. eventually the black hole will evaporate completely. So, what happened to the information in your book if it is lost forever when the black hole vanishes? That violates a sacred principle of quantum mechanics. This is the paradox. To solve it, physicists have proposed ideas that sound like science fiction. One radical suggestion is the firewall hypothesis. It argues that instead of a smooth passage across the event horizon, an infalling astronaut would encounter a searing wall of high-energy particles, a literal firewall that would incinerate them. This protects information from being lost but blatantly contradicts Einstein's prediction of a smooth, uneventful horizon. Another, more elegant idea comes from the holographic principle. It suggests that all the information about everything that falls into a black hole is not lost inside, but is somehow encoded on the two-dimensional surface of the event horizon like a cosmic hologram. The three-dimensional interior, including the singularity, is a projection of that information. In this view, the universe itself might be a hologram, with all the information of our three-dimensional reality stored on a distant two-dimensional surface. Perhaps the most profound connection is known as AR equals EPR. This conjecture, born from the minds of leading theorists, proposes a direct link between two of the strangest phenomena in physics, black holes and quantum entanglement. It suggests that two entangled particles, which can instantaneously affect each other across vast distances, might be connected by microscopic wormholes or Einstein-Rosen bridges through spacetime. This implies that the fabric of space and the phenomenon of quantum entanglement are two sides of the same coin. Inside a black hole, the very geometry of space may be woven from a dense web of quantum connections. So the black hole is no longer just a cosmic vacuum cleaner. It is a laboratory for the most extreme physics, a place where gravity and quantum mechanics meet in a violent clash. It is a prison from which nothing escapes, yet it may hold the key to understanding how information, the most fundamental currency of reality, is woven into the fabric of space and time. We are left staring at the ultimate dark mirror, wondering if it hides a firewall, a hologram, or a gateway to a deeper layer of existence we cannot yet see. The black hole's event horizon is a one-way door into a place where time itself is crushed. But what if the universe contains doors that swing both ways, not just through space, but through time? The seventh great cosmic question asks, is time travel possible? For decades, this idea lived solely in the realm of science fiction. Yet, when we look at the equations of Einstein's general relativity, the universe seems to leave the door ever so slightly ajar. The theory describes gravity not as a force but as the warping of spacetime by mass and energy. In extreme configurations, this warping could, in principle, create paths that loop back on themselves. Physicists call these closed time-like curves. They are not machines built in a garage but potential features of the cosmic landscape. One famous example is the wormhole, a theoretical tunnel connecting two distant points in spacetime. If one mouth of the wormhole could be moved at near light speed or placed in a region of intense gravity, time would pass more slowly for it relative to the other mouth. Step into the accelerated mouth in the year 3000, and you might exit the stationary mouth in the year 2000. You have traveled to the past through a shortcut in the fabric of reality. Another hypothetical structure is an infinitely long, incredibly dense cosmic string, spinning at nearly the speed of light. The immense gravitational whirlpool around it could twist spacetime into a loop, allowing a spacecraft on a precise trajectory to circle back and meet its own past. These are not fantasies, but mathematically valid solutions to Einstein's own equations. However, the moment we consider a traveler interacting with their own past, we hit the infamous grandfather paradox. What if you went back in time and prevented your own grandfather from meeting your grandmother? You would never be born, so you could never go back in time to stop the meeting, which means you would be born, and so on. It is a logical contradiction that seems to make time travel impossible. Physics offers a few breathtaking ways out. The first is the Novikov self-consistency principle. It proposes that the laws of physics simply will not allow a paradox to happen. Any action you take in the past was always part of history. You might intend to change the past, but something will always intervene to ensure events unfold exactly as they always did. In this view, time is a single, immutable story. You cannot change a chapter because you were always a part of it. The second, and even more radical, escape route is the many worlds interpretation of quantum mechanics. Here, every possible outcome of every event actually happens, but in a newly branching parallel universe. In this scenario, if you travel to the past and alter an event, you do not change your own history. Instead, you create a fork in the road, branching off into a new, separate timeline where those new events play out. Your original timeline remains untouched. The paradox is avoided because you are not changing the past of your own universe. You are merely visiting the past of another. So, does this mean we could build a time machine? The practical barriers are almost certainly insurmountable. To stabilize a wormhole against instant collapse would require a form of matter with negative energy density, something we have never seen in macroscopic amounts. A rotating cosmic string would need to be thinner than an atom, but with the mass of an entire galaxy. The energy requirements are beyond any conceivable civilization. For any human-sized object, time travel to the past almost certainly remains in the realm of mathematical curiosity. Yet for the tiniest particles, the rules might be different. Some experiments in quantum mechanics already show particles behaving as if they are influencing their own past, a phenomenon called retrocausality. While this is not a person hopping into a phone booth, it hints that on the most fundamental level, the arrow of time might be more flexible than our everyday experience suggests. We are left with a universe whose deepest laws do not explicitly forbid traveling to the past, yet whose practical construction seems to guard it with impossible walls. Time travel may be written into the fine print of reality, in a language we can read but cannot yet speak. The paradox of time travel rests on a logical impossibility, a closed loop where cause and effect unravel. Yet the universe we inhabit is built upon a sequence of causes and effects so profound it led to us. This brings us to the eighth monumental question, a pivot from the cosmic to the deeply personal. How did life begin? We are faced with the ultimate alchemical mystery, the transformation of inert matter into a living, self-replicating system. This leap from chemistry to biology is called abiogenesis, and it represents one of the widest gaps in our scientific understanding. We know the ingredients that were present on the young Earth, a swirling broth of water, methane, ammonia, and hydrogen, energized by lightning, volcanic heat, and ultraviolet light from the sun. The challenge is understanding how those simple molecules arranged themselves into the breathtaking complexity of the first living cell. In the 1950s, a landmark experiment tried to recreate those ancient conditions. Stanley Miller and Harold Urey sealed those basic gases in a glass apparatus, zapped them with electrical sparks to simulate lightning, and within days the clear water turned a murky brown. When they analyzed it, they found amino acids, the fundamental building blocks of proteins, which are essential for life as we know it. It was a stunning result, proving that the organic ingredients for life could form naturally from simple chemistry. But making the bricks is a far cry from building the cathedral. The next steps are where the mystery deepens. How did these amino acids link into long chains? How did they become encapsulated within a protective membrane? And most crucially, how did a molecule arise that could not only carry information but also copy itself? The leading hypothesis to answer this final puzzle is known as the RNA world. Today, life uses DNA as its permanent genetic library and proteins as its molecular machines to do the work. But RNA is a remarkable jack of all trades. It can store genetic information like DNA and catalyze chemical reactions like a protein. the idea is that before DNA and proteins existed, there was an early world dominated by self-replicating RNA molecules. These molecules would have competed for resources, evolved through natural selection at the chemical level, and eventually learned to build protective cells and create more efficient systems, ultimately giving rise to the DNA-protein-based life we see today. Scientists have even created RNA molecules in the lab that can catalyze their own replication, a tantalizing glimpse at how this might have happened. Yet the path from a self-replicating strand of RNA to even the simplest bacterium is astronomically complex and filled with unknown steps. This profound difficulty has led to another compelling idea, panspermia. Perhaps life did not begin on Earth at all, but was seeded here from elsewhere. The theory suggests that hardy microbial life could survive a journey through space, protected inside rocks blasted off a planet like Mars by an asteroid impact. These meteorites could then travel through the solar system and crash land on a young, habitable world like Earth, delivering the spark of life. We have evidence that the building blocks of life, including complex organic molecules and even amino acids, are found on asteroids and in the vast molecular clouds between the stars. The universe seems preloaded with life's raw materials, but panspermia, while moving the problem to another location, does not solve it. It simply pushes the question of origins onto another world, perhaps one with more favorable conditions for that first miraculous assembly. So we are left with a puzzle of staggering proportions. We have outlined a plausible sequence from cosmic chemistry to organic bricks to self-replicating molecules. But the moment of transition, the precise spark that turned chemistry into biology, remains hidden in the deep past. It is the silent hinge upon which all of history turns. Finding the answer would tell us if life is a bizarre, one in a trillion accident on a lonely planet, or if it is as natural and inevitable a part of the cosmos as the formation of stars. The spark of life leads to an even deeper mystery, one that burns within each of us. What is the nature of consciousness? You are not just a collection of atoms and electrical signals. You are a living, breathing universe of experience. You feel the warmth of sunlight, the sting of a cut, the weight of a memory. This inner world of subjective feeling is what philosophers call qualia, and it presents science with its most intimate puzzle. How does the 3-pound lump of wet tissue inside our skulls give rise to the rich, private movie of our existence? This is known as the hard problem of consciousness. We can map which brain regions light up when you see the color red. We can trace the neural pathways of fear or love. But we cannot explain why those electrical patterns are accompanied by the actual, felt experience of redness or the visceral pang of emotion. It is the gap between objective process and subjective reality, and it remains a chasm. The dominant scientific view is materialism. It holds that consciousness is an emergent property, a novel phenomenon that arises when a system, like the human brain, reaches a certain level of complex, integrated information processing. In this view, the brain is a biological computer, and the mind is the software it runs. There is nothing magical or extra, just an astonishingly intricate network of nearly 100 billion neurons communicating in a symphony of electrochemical pulses. Yet, this explanation leaves the hard problem untouched. Why should any amount of information processing, no matter how complex, feel like anything from the inside? This difficulty has led some thinkers to a radical alternative, panpsychism. This idea proposes that consciousness is not something that emerges at a certain level of complexity, but is a fundamental property of the universe like mass or charge. In its most basic form, it suggests that even elementary particles possess some tiny, primitive form of experience or proto-consciousness. An electron would not have thoughts or feelings, but perhaps a bare, minimal spark of subjective interiority. When these particles combine into more complex systems like brains, these tiny sparks of experience combine and amplify into the rich consciousness we know. It is a humbling, even beautiful thought. The screen you're looking at, the air you breathe, the distant stars, all might possess some faint whisper of inner life. This idea inevitably leads to a staggering cosmic question. Could the universe itself be conscious? If consciousness is woven into the fabric of reality, then the cosmos, with its vast, interconnected networks of galaxies linked by gravity and dark matter, might constitute a system of unimaginable complexity. Could it harbor a mind of its own, a slow cosmic consciousness operating on timescales of billions of years, contemplating itself through the eyes of the life it has spawned? We are left gazing inward and outward simultaneously, caught between two visions of reality. In one, we are lonely islands of awareness in a vast, insensate machine. In the other, we are droplets of a universal ocean of mind, temporarily separated, yet fundamentally connected to the consciousness of everything that is. The mystery of our own inner light may be the key to understanding whether the cosmos is merely a grand clockwork mechanism or a living, thinking entity in the process of awakening. The profound question of consciousness, whether it is an emergent illusion or a fundamental cosmic fabric, inevitably leads us to an even more unsettling possibility about the nature of reality itself. Is the universe a simulation? This is not a plot from a science fiction movie, but a serious philosophical argument put forward by thinkers like Nick Bostrom. He frames it as a stark trilemma, three possibilities of which at least one must be true. First, that almost every intelligent civilization goes extinct before reaching a technological stage capable of creating realistic simulations. Second, that any civilization which does reach that post-human stage has absolutely zero interest in running simulations of its own history. Or third, that we are almost certainly living in a computer simulation created by our advanced descendants. If you reject the first two ideas, that civilizations survive and are curious, then the logical conclusion is the third. A post-human civilization could, in principle, create astronomically many detailed simulations of its ancestors. The simulated minds would vastly outnumber the original biological ones. Therefore, if such simulations are possible and are run, the odds are overwhelming that any given conscious experience like yours right now is happening inside one. It is a statistical argument that is chillingly difficult to dismiss. But if we are in a simulation, could we ever find evidence? Scientists have proposed looking for potential glitches in the code of reality. Just as a video game has a finite resolution, our universe might reveal a pixelated structure at the smallest scales. Some theories of quantum gravity suggest that space and time themselves are not smooth and continuous, but quantized into tiny, indivisible units like the pixels on a screen. Finding such a fundamental graininess could be a signature of a simulated reality. Another place to look might be in the fundamental constants of nature. Are the speed of light or the strength of gravity perfectly tuned, or do they show rounding errors? We might also examine high-energy cosmic rays. There is a known limit called the Greisen-Zatsepin-Kuzmin cutoff, a theoretical energy ceiling for cosmic rays from distant sources due to interactions with the cosmic microwave background. If we find particles with energies beyond this cutoff, it could suggest the simulation's physics engine has a bug or a simplification. The implications of this hypothesis are philosophically seismic. If our reality is a simulation, then the laws of physics are not fundamental truths, but merely the rules of the program which could be changed or updated. The concept of free will becomes deeply ambiguous. Are our choices our own, or are they the output of a deterministic algorithm running on some unfathomable hardware? It reframes existence itself, suggesting that the stars, the planets, and the very atoms in your hand might be nothing more than information, elegantly rendered for an audience we cannot perceive. Yet, for all its logical pull, the simulation hypothesis ultimately pushes the question of origins one step back. It does not answer where the simulating civilization came from or what reality their universe is made of. We are left in a hall of mirrors, wondering if we are the dreamers or the dream. This hall of mirrors, where reality itself might be a rendered illusion, forces us to confront a far more immediate mystery. Why does anything exist at all? This is not a philosophical abstraction, but a razor-sharp scientific question. Our universe is made of matter, from the planets and stars to the very atoms in your body. But according to our best theories, it should not be here. This leads us to our 11th great cosmic question: why is there more matter than antimatter? The story begins, as so many do, with the Big Bang. In that searingly hot, dense beginning, energy should have crystallized into perfectly equal amounts of matter and its mirror opposite, antimatter. For every quark, there should have been an antiquark, for every electron, a positron. These are not just theoretical ideas. We can create antimatter in our laboratories today. And when matter and antimatter meet, they annihilate each other in a flash of pure energy, leaving nothing behind. So, if the Big Bang produced a perfectly symmetrical creation, all those particle-antiparticle pairs should have found each other almost instantly. The entire universe would have vanished in a spectacular flash of gamma rays, leaving behind an eternal, featureless sea of radiation, a cosmic reset to absolute zero. Yet here we are. Clearly, that did not happen. Something tipped the scales. Out of every 10 billion particles created in the primordial fireball, roughly 1 extra particle of matter survived. That 1 in 10 billion imbalance is the reason for everything you see. Every galaxy, every star, every living creature is made from that tiny surplus, the leftover ash from an almost perfect annihilation. This cosmic favoritism is known as the Barrian asymmetry problem. To explain it, physicists identified 3 necessary conditions named after the scientist Andrei Sakharov. First, there must be a process that does not treat matter and antimatter equally, a phenomenon called charge parity violation or CP violation. Second, the universe must have been out of thermal equilibrium, meaning it was changing and cooling, not static. And third, these processes must not conserve Barrian number, which is a fancy way of saying they must be able to create more matter than antimatter. The hunt has been on for decades to find a process that meets all these conditions. And we have found a piece of the puzzle. In giant particle accelerators like the Large Hadron Collider, scientists have observed CP violation in the decay of certain exotic particles like kaons and B mesons. It is a real, measurable effect. The laws of physics in very specific circumstances do show a slight bias, but here is the crushing disappointment. The amount of CP violation we have measured in all our experiments is pitifully small. It is like finding a single grain of sand on a beach and declaring it the cause of the entire coastline. The asymmetry we see is billions of times too weak to account for the overwhelming dominance of matter in our universe. So the mystery deepens. We have found the signature of the crime, but the weapon we found is not nearly powerful enough to have committed it. The true source of the cosmic imbalance must lie elsewhere, in physics beyond our current standard model. Candidates abound. It could be linked to the mysterious neutrino. If these ghostly particles are their own antiparticles, a process called neutrino oscillation in the early universe could have generated the surplus. It might be tied to the inflationary period, a fraction of a second after the Big Bang when the universe expanded exponentially, potentially magnifying a tiny asymmetry into the one we see today. Or it could involve hypothetical particles predicted by grand unified theories, which existed only at energies so high we may never recreate them. The stakes could not be higher. This is not just a question about particles, it is the question of our own existence. We are the children of that 1 in 10 billion anomaly. Finding the complete answer would tell us why the universe chose to become a place of substance and structure, rather than fading into silent, empty light. It is a search for the original fingerprint on reality, the reason there is something rather than nothing. The very matter that makes us possible is a ghost of a cosmic imbalance, a slight warp in the rules of creation. But that warp exists within a grander structure, a canvas of space itself whose true nature remains hidden. The 12th great question asks, what is the true size and shape of the universe? We are not asking about the observable universe, the sphere of light that has had time to reach us in 13.8 billion years. We are asking about the totality of everything that exists, the entire cosmic stage. Is it infinite, stretching forever in all directions, or is it finite but without an edge, like the surface of a balloon? The answer depends on the universe's geometry, a concept governed by its density. Imagine space itself as a vast, flexible sheet. There are 3 possible shapes it could take, each tied to the cosmic tug of war between expansion and gravity. The first is a flat geometry. This is the familiar world of Euclid, where parallel lines never meet and the angles of a triangle always add up to 180 degrees. A flat universe would have just the right density, a perfect balance point called the critical density, to eventually halt its expansion after an infinite amount of time, but only just barely. The second possibility is a spherical or closed universe. If the density is higher than the critical value, gravity wins. Space curves in on itself like the surface of a sphere. On a sphere, parallel lines eventually cross, and a triangle's angles add up to more than 180 degrees. A closed universe would be finite, but you could travel in one direction forever and end up back where you started, just as a ship sailing west on Earth eventually returns from the east. The third shape is hyperbolic or open. If the density is too low, the universe curves outward like a saddle. Here, parallel lines diverge and triangles have angles summing to less than 180 degrees. An open universe would be infinite and expand forever. For decades, this was one of cosmology's great debates. Then we measured it by meticulously studying the faint afterglow of the Big Bang, the cosmic microwave background radiation. Satellites have mapped the tiny temperature fluctuations imprinted on the sky. The pattern of these hot and cold spots acts like a cosmic ruler. The results are astonishingly precise. The universe, as far as we can measure, is geometrically flat. Not just roughly flat, but flat too, within a razor-thin margin of error. This seems to settle the question, but flat geometry presents 2 breathtaking and very different possibilities. A flat universe can be infinite, extending without end in all directions. Or it can be finite but multiply connected, like a video game screen where if you fly off one edge, you reappear on the opposite side. Think of a classic arcade game like Asteroids. Your ship can fly off the top of the screen and instantly reappear at the bottom. The screen is finite, but it has no boundary. It is wrapped into a torus or donut shape. Could our 3-dimensional universe be shaped like a 4-dimensional donut? This is not a joke, it is a serious topological possibility. In such a universe, if you had a telescope powerful enough, you might see duplicate images of the same galaxy in different parts of the sky, because the light from it has taken multiple paths around the cosmos to reach you. It would be like seeing your own reflection in a hall of mirrors, but on a cosmic scale. Astronomers have searched for these ghostly duplicates, these matching patterns of galaxy clusters on opposite sides of the sky. So far, they have found none. But that does not rule out the possibility that the universe is simply so vast that the wrapping occurs on a scale larger than our observable horizon. We are like ants on a giant beach ball, able to see only a small, flat patch of sand, with no idea the surface curves back on itself, so we are left with a profound irony. We have measured the geometry of our cosmic home with incredible accuracy and found it to be flat. Yet we still do not know if we live in an infinite plane or a finite closed loop. The true shape of all that exists may be forever hidden behind the veil of the cosmic horizon, a final frontier that light itself has not yet had time to cross. The shape of our universe, whether infinite or curled into a hidden topology, hints at a reality far stranger than the 3 dimensions we experience every day. This leads us to a question that feels like it belongs in a fantasy novel, yet is a serious pursuit of modern physics. Do other dimensions exist? We are intimately familiar with the three spatial dimensions of length, width, and height, the stage upon which all action unfolds. But for nearly a century, theoretical physicists have proposed that our universe may be a slice of something much grander, a higher dimensional reality. The idea first gained traction in the 1920s with the work of Theodore Kaluza and Oskar Klein. They showed that if you rewrote Einstein's equations of gravity in a hypothetical universe with one extra tiny spatial dimension, a remarkable thing happened. The equations for electromagnetism, the force governing light and electricity, emerged naturally from the geometry of that hidden dimension. It was a stunning unification, suggesting that the fundamental forces might just be the geometry of a higher dimensional space. But if there is a fourth spatial dimension, where is it? Why can't we walk into it? The Kaluza-Klein theory proposed that this extra dimension is compactified, or curled up, on a scale so unimaginably small that it is completely invisible to us. Think of a garden hose. From a distance, it looks like a simple one-dimensional line, but up close you see its circular cross-section, a second dimension curled into a tiny loop. To an ant living on the hose, moving along its length is easy, but moving around its circumference is a microscopic journey. Our universe, according to this idea, could be like that hose, with extra dimensions curled up at every point in space into shapes called Calabi-Yau manifolds. These are intricate, multi-dimensional shapes with 6 or 7 dimensions curled upon themselves, determining the properties of particles and forces in our three-dimensional world. This idea finds its most advanced expression in string theory. For the mathematics of string theory to be consistent, to avoid nonsensical infinities, it requires more than just 3 dimensions of space and 1 of time. The most popular versions demand 10 or 11 total dimensions. That means there could be 6 or 7 extra spatial dimensions, all compactified at the Planck scale, a distance a billion times smaller than an atomic nucleus. In this view, the fundamental particles we see are not points, but incredibly tiny, vibrating loops of energy, strings. The pitch and pattern of a string's vibration as it moves through these hidden dimensions determines whether it manifests as an electron, a quark, or a photon. The entire symphony of the universe is played on these multidimensional strings. If these extra dimensions are real, could we ever detect them? Scientists at the Large Hadron Collider are actively searching for clues. One signature would be missing energy. If 2 protons collide with tremendous force, they could produce a particle that briefly escapes into an extra dimension, carrying away energy and momentum before returning to our familiar 3-dimensional space. Our detectors would see an imbalance, energy that simply vanishes. Another, even more dramatic possibility is the creation of microscopic black holes. In a universe with large extra dimensions, gravity could become much stronger at tiny scales, making it possible for the collider to briefly stitch together a black hole smaller than an atom, which would instantly evaporate in a shower of particles. While such an event has not been observed, the search continues. The very possibility reshapes our cosmic perspective. We may be like fish in a pond, completely unaware of the world above the water's surface, yet living in a reality defined by its depth. Those hidden dimensions, if they exist, are the true architects of reality, the reason why the laws of physics are what they are, and why our universe has the particular form we call home. That hidden architecture of reality, with its potential extra dimensions, brings us back to the most explosive moment of all. What powered the Big Bang? We have traced the cosmic story back to a hot, dense fireball, but the ultimate origin of that fireball remains shrouded in mystery. The moment of the Big Bang itself is described as a singularity, a point of infinite density and temperature where the known laws of physics, specifically Einstein's theory of general relativity, completely break down. It is not just that we do not know what happened, it is that our equations yield meaningless infinities, a clear sign that we are missing a crucial piece of the puzzle. To understand the birth of our universe, we must look to an even more fleeting and bizarre epoch that came immediately after. This is the theory of cosmic inflation. In the tiniest fraction of a second following the initial moment, the universe is thought to have undergone a period of exponentially faster than light expansion. Space itself stretched by a factor of at least 10 to the power of 26 in less than a billionth of a billionth of a billionth of a second. This incredible burst of growth solved several major puzzles in cosmology. It explains why the universe appears so uniform in all directions, why it is geometrically flat, and how the seeds for all future structures like galaxies were planted. But what could possibly fuel such an outrageous event? The leading candidate is a hypothetical energy field called the inflaton field. Think of it like a cosmic landscape with hills and valleys. In the earliest moments, this field was stuck in a high-energy state, like a ball perched precariously on a steep hilltop. The energy density of this false vacuum state had a repulsive gravitational effect, causing space to expand at a furious, exponential rate. This was the inflationary epoch. As the field slowly rolled down the hill, it released its pent-up energy, reheating the universe and filling it with the hot soup of particles of the traditional Big Bang. The tiny quantum fluctuations in this field as it rolled became the density variations that, over billions of years, grew into the cosmic web of galaxies we see today. But this only pushes the question one step further back. What set off inflation in the first place? What was the match that lit this cosmic fire? Here, physics ventures into truly speculative, yet mathematically grounded territory. One idea is that our universe is not the only one. In the framework of eternal inflation, the inflaton field may have different values in different regions of a pre-existing, perhaps eternal, space-time. Our entire observable cosmos is just one bubble of lower energy that formed when the field in our region decayed, while other regions continue inflating forever, giving rise to a vast, frothing multiverse of disconnected bubble universes, each with potentially different physical laws. Another breathtaking possibility comes from string theory, specifically a version called M-theory. Here, our three-dimensional universe could be a membrane or brain floating in a higher dimensional space. The Big Bang might have been triggered by a cataclysmic collision between two such brains. The immense kinetic energy of that collision, translated into our three-dimensional world, would appear as the searing heat and rapid expansion of the beginning. In this view, the Big Bang was not a beginning from nothing, but a transformation from a pre-existing state in a higher dimensional reality. Perhaps the most profound idea of all is that the universe and even space-time itself could have quantum-tunneled into existence from literally nothing. Not empty space, but the absence of space, time, and matter altogether. In quantum mechanics, particles can spontaneously appear from a vacuum due to uncertainty. Extending this to the cosmos, a tiny bubble of false vacuum containing a universe in embryonic form could have tunneled into existence through a quantum fluctuation. Once it appeared, its internal inflaton field would have driven the explosive inflation that created everything we know. In this scenario, the question of what came before may have no meaning because time itself emerged with the bubble. So we circle back to the ultimate singularity, not with an answer but with a spectrum of profound possibilities. Was our universe born from a quantum tremor in an eternal multiverse, a shattering collision in a hidden dimension, or a spontaneous leap from absolute nothingness? The engine of creation remains hidden behind the veil of the Planck epoch, a realm where only a theory of quantum gravity can guide us. For now, the power behind the Big Bang is the deepest silence at the heart of all our cosmic questions. The engine of creation, hidden at the Planck scale, represents the final frontier of our understanding, a place where our two most successful theories of reality enter into open war. This brings us to the 15th monumental question: what is quantum gravity? It is the single greatest unsolved problem in theoretical physics, the quest to unify Einstein's majestic theory of general relativity with the bizarre, probabilistic rules of quantum mechanics. These two pillars of modern science are both spectacularly accurate in their own domains, yet they are fundamentally, catastrophically incompatible. General relativity describes gravity not as a force, but as the elegant curvature of a smooth, continuous spacetime, a flexible stage upon which the cosmic drama plays out. The quantum world, governing particles and forces, is everything but smooth. It is a realm of discrete packets of energy, inherent uncertainty, and ghostly probabilities, where particles can be in two places at once and empty space seethes with temporary particles flickering in and out of existence. The conflict is stark in the heart of a black hole or the first instant of the Big Bang, where gravity becomes unimaginably strong and volumes become vanishingly small. We need a theory that can describe a curving, dynamic stage that is also inherently grainy and probabilistic. Our current equations simply explode into nonsense. To resolve this, physicists are constructing breathtaking new visions of reality. One of the most famous is string theory. It proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy, strings. Just as different vibrations of a violin string produce different musical notes, the distinct vibrational patterns of these fundamental strings would give rise to all the particles and forces we see, from electrons to photons. Crucially, one specific vibrational mode of the string naturally corresponds to the graviton, the hypothetical quantum particle that would carry the force of gravity. In this framework, gravity is woven into the same tapestry as the other forces. However, for the mathematics to work, string theory requires extra spatial dimensions curled up into complex microscopic shapes. The other major contender is loop quantum gravity. It takes a radically different approach. Instead of changing the actors on the stage, it changes the stage itself. This theory proposes that space itself is not smooth and continuous, but is woven from a network of finite, discrete loops. Picture the fabric of reality not as a smooth sheet, but as a vast, intricate spiderweb, with the threads representing tiny, indivisible quanta of area and volume. Space is literally pixelated, but at a scale a billion times smaller than an atomic nucleus. In this view, the smooth spacetime of general relativity emerges as an average of this frenetic quantum weave, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. Gravity then arises naturally from the interactions and evolution of this quantum geometry. Both theories are monuments of human ingenuity, yet they face a daunting, perhaps insurmountable, challenge: testing. Their predictions become significant only at the Planck scale, a realm of such unimaginably small distances and high energies that it is completely inaccessible to any conceivable particle accelerator we could build. It is like trying to understand the structure of a snowflake by throwing mountains at it. The energies are all wrong, so we search for indirect clues. Scientists scrutinize the cosmic microwave background for imprints from the universe's first moments, when quantum gravity effects may have left a faint signature. They study the Hawking radiation from black holes, looking for deviations that might reveal the quantum structure of spacetime at the event horizon. The goal is to find a cosmic fossil, a remnant from an era when gravity and the quantum world were one. Until then, we are left with two magnificent yet unproven visions of ultimate reality, one built from vibrating strings in a hidden dimensional arena, the other from a tapestry of woven space. The search for quantum gravity is the search for the single rulebook from which all of creation is written. The search for a single rulebook of reality inevitably leads us to doorways in the fabric of space and time that seem ripped from fantasy. Are there white holes and wormholes? These are not mere science fiction, but legitimate, if exotic, mathematical solutions to Einstein's own equations of general relativity. They represent the universe's potential for architecture far stranger than we can observe. Let us begin with the white hole, the black hole's theoretical twin. If a black hole is a region of space from which nothing, not even light, can escape, then a white hole is its perfect time reversal. It is a region of space into which nothing can enter, but from which matter and energy can only emerge. Imagine a cosmic fountain eternally gushing out material, yet completely impervious to anything trying to fall back in. Mathematically, if you were to take the equations for a black hole and run the clock backwards, you would get a white hole. This symmetry is beautiful, but it creates a profound problem with the second law of thermodynamics, which states that disorder or entropy always increases. A white hole spewing out ordered material from seemingly nothing would appear to decrease entropy, violating this fundamental cosmic rule. Because of this, most physicists believe that while white holes are mathematically permissible, they are physically unstable. Any speck of dust attempting to fall into one would, in theory, cause it to collapse instantly into a black hole. They may be fascinating ghosts in the equations, but they are unlikely to exist in our stable universe. Yet, they force us to consider the flexibility of time and causality in the extreme landscapes of gravity. If white holes are one-way exits, then wormholes promise two-way travel. Formerly known as Einstein-Rosen bridges, these are theoretical tunnels connecting two distant points in space-time. Picture the universe as a vast, flat sheet of paper. To get from a dot on one side to a dot on the other, you would have to travel the long way across the entire page. But if you could fold the paper so the two dots touched and then pierce through the fold, you would create a shortcut, a wormhole. This is not just a spatial shortcut, it could be a temporal one as well. If one mouth of the wormhole was moved at near light speed or placed in a strong gravitational field, time would pass more slowly for it. You could step into that mouth in the year 3000 and exit the other mouth in the year 2000, effectively traveling to the past. The catch, and it is a monumental one, is stability. According to general relativity, any wormhole that could be used for travel would be incredibly unstable. It would pinch shut the instant anything tried to pass through, like a bubble collapsing. To hold it open, you would need a substance that exerts negative pressure, a kind of anti-gravity. This hypothetical material is called exotic matter. We are not talking about dark matter, but something even stranger with negative energy density. While tiny amounts of negative energy can be generated in the lab through quantum effects like the Casimir effect, the quantities needed to stabilize a human-sized wormhole are beyond astronomical. They may simply be impossible. However, the theoretical pursuit of wormholes has led to one of the most profound connections in modern physics. Recent work suggests a deep link between wormholes and quantum entanglement, the spooky connection where particles instantly influence each other across vast distances. The conjecture, known by the shorthand ER equals EPR, proposes that two entangled particles might be connected by a microscopic wormhole. In this view, the fabric of spacetime itself could be woven from a vast network of these quantum connections. The wormhole, then, is not just a shortcut for spaceships, but a fundamental feature of how the universe stitches itself together at the quantum level. So we are left with a breathtaking duality. On one hand, traversable wormholes for starships almost certainly remain in the realm of mathematics, blocked by the need for impossible amounts of exotic matter. On the other, they may be everywhere at the smallest scales, the hidden threads of quantum gravity that bind reality into a coherent whole. These cosmic doorways challenge our understanding of connectivity, suggesting that the distance between 2 points may be an illusion, and that the deepest links in the universe are not across space but through it. These cosmic doorways, woven from the fabric of spacetime itself, are silent and invisible to our eyes, but the universe also speaks in sudden, deafening shouts across the radio spectrum. What causes fast radio bursts? In the last 2 decades, astronomers have stumbled upon one of the most explosive and puzzling phenomena in the cosmos. Fast radio bursts, or FRB, are exactly what their name suggests: incredibly brief, intensely powerful flashes of radio waves that last only a few thousandths of a second. In that fleeting moment, a single burst can release more energy than our sun puts out over 80 years. They arrive from galaxies billions of light years away, a signal that has crossed half the observable universe to briefly flicker in our telescopes. The first one was discovered in 2007, buried in archival data from a radio telescope in Australia. For years, it was considered a bizarre, one-off anomaly, perhaps a glitch in the equipment. But then we found more, and we realized the sky is crackling with these cosmic firecrackers. Some burst once and are never heard from again, a solitary scream in the dark. Others repeat, but with a maddening, unpredictable cadence, sometimes quiet for months before erupting in a frantic storm of pulses. This repetition is a crucial clue, ruling out any source that destroys itself in the process, like a single, cataclysmic stellar explosion. So what celestial engine can produce such a staggering amount of energy in such a vanishingly short time? The prime suspect today is a magnetar. Imagine the core of a giant star, more massive than our sun, collapsing into a city-sized ball of ultra-dense neutrons. Now compress its magnetic field 1 trillion times over. The result is a magnetar, a neutron star with a magnetic field so intense it could strip the information from every credit card on Earth from halfway across the solar system. Theorists suggest that starquakes on the surface of a magnetar, or sudden rearrangements of its insane magnetic field, could unleash titanic blasts of radiation, including those brief, focused radio pulses we see as FRBs. In 2020, we caught one in the act, a magnetar within our own galaxy, known as SGR 1935 plus 215, erupted in a burst of radio waves that looked, for all intents and purposes, like a weaker version of a cosmic FRB. It was a smoking gun, strongly suggesting that at least some of these mysterious signals come from these magnetic monsters. But are magnetars the whole story? Other potential sources remain on the table. The collision and merger of 2 neutron stars, a cataclysm that also produces gravitational waves, could generate a one-time, spectacular burst. Some repeating FRBs even show a strange periodicity, a faint rhythmic pattern in their eruptions, which might point to a highly magnetized neutron star orbiting in a binary system with another star, its outbursts triggered at a specific point in its orbit. And then, of course, there is the most speculative idea of all, one that scientists must consider and then cautiously set aside: advanced alien technology. Could these be signatures of immense interstellar beacons, or the power streams of light sails on a cosmic scale? While there is no evidence to support this, and natural explanations are far more likely, the sheer power and brevity of the signals force us to acknowledge the possibility, however remote. The hunt for answers is accelerating, driven by new telescopes like CHIME, the Canadian Hydrogen Intensity Mapping Experiment. Unlike traditional dishes that point at one part of the sky, CHIME is a stationary array of metal cylinders that stares at the entire overhead sky each day. It is a fire hose of data, and it is detecting new FRBs by the dozens, mapping their locations and characteristics with unprecedented speed. Each new detection is a piece of the puzzle, helping us classify them and trace them back to their host galaxies, often small, faint, and turbulent dwarf galaxies where star formation is rampant and magnetars may be born. Yet for all our progress, the precise physical mechanism, the exact trigger that launches these radio tsunamis across the universe, remains locked inside some of the most extreme environments imaginable. We are listening to the cosmos crackle with messages we can now hear, but are only just beginning to understand. These brief, violent radio shouts from magnetars are signals from the present-day universe, a cosmic now. But to find a potential crack in the very foundations of cosmology, we must look back to the oldest light of all and discover a pattern that seems to whisper of a time before time. This brings us to our 18th great question. What is the axis of evil in the cosmic microwave background? The cosmic microwave background, or CMB, is the faint, cold glow that fills the entire sky. It is the cooled and stretched remnant of the fireball of the Big Bang, a snapshot of the universe when it was a mere 380,000 years old, a cosmic baby picture. According to our most cherished principles, this afterglow should be the same in all directions, a nearly uniform sea of microwaves with only tiny, random fluctuations. This assumption of uniformity is enshrined in the cosmological principle, which states that on the largest scales, the universe is homogeneous and isotropic, meaning it looks the same in every direction and from every location. There should be no up or down, no left or right, no special axis to the cosmos. But what if there is? When scientists created exquisitely detailed maps of the CMB using satellites like WMAP and Planck, they made a startling and deeply unsettling discovery. The temperature fluctuations, those hot and cold spots that seeded all future galaxies, are not completely random. On the very largest scales, larger than the observable universe itself should allow, these fluctuations appear to align along a particular preferred direction in space. Researchers half-jokingly, half-nervously dubbed this alignment the axis of evil. The name captures the profound threat it poses to our standard model. It is as if you painted a perfectly random splatter pattern on a sphere, but then stepped back and realized all the largest splotches lined up along a single, invisible seam. This should not happen. In a universe born from a chaotic quantum froth and inflated to smoothness, there should be no memory of direction, no cosmic compass pointing a preferred way. So what could this axis mean? The first and most conservative explanation is that it is not real at all, but a phantom born from our own vantage point. Perhaps it is an artifact of how we subtract the blinding glare of our own Milky Way galaxy from the data, or an unrecognized systematic error in the satellite instruments. After all, we have only one universe to observe, and from our single, fixed location within it, certain statistical flukes might appear significant even when they are not. Scientists have wrestled with this possibility for years, meticulously checking and rechecking the data. Yet the peculiar alignments persist, stubbornly resisting dismissal as mere noise. If the axis of evil is real, the implications are revolutionary. It could mean the cosmological principle is wrong, or at least not the whole story. Our universe, on its grandest scales, might have a fabric with a subtle grain, a preferred orientation imprinted upon it from the very beginning. This points to possibilities that stretch the imagination. One is that the universe is not isotropic because it is rotating. A slight overall spin to the entire cosmos could have imparted a directional preference to the primordial plasma, leaving its fingerprint in the CMB. Another, even more profound idea is that this axis is a relic from a time before the Big Bang. If our universe was born from a collision of higher dimensional brains, as some string theory models suggest, that collision would not have been perfectly symmetric. It could have imparted a directional preference that survived inflation and was frozen into the CMB. Alternatively, if we live in a universe with a non-trivial topology, if it is wrapped into a finite shape like a giant donut, the light from the CMB could wrap around that structure, creating repeating patterns and large-scale correlations that look like an axis from our limited perspective. The axis of evil, then, is not just a statistical anomaly. It is a potential window into the ultimate geometry of all that exists, and a hint that the cosmos remembers something from beyond the inflationary veil. It challenges the comforting idea that we live in a perfectly smooth, featureless, and random universe. Instead, it suggests the cosmic canvas might have a hidden texture, a whisper of structure so vast we can only see its faintest echo in the oldest light there is. The search for an answer is a search for our true place in the cosmos. Are we in a universe that is fundamentally the same everywhere, or one that has a silent, monumental spine we are only just beginning to sense? That silent, monumental spine of the cosmos points to an even more profound and personal mystery. Why does the universe seem perfectly tailored for our existence? The fundamental constants of nature, the numerical values that govern the strength of gravity, the power of the nuclear forces, and the density of dark energy, appear to be exquisitely fine-tuned. Change any one of them by just a hair, and the universe as we know it would not exist, and neither would we. If the strong nuclear force which binds atomic nuclei together were a few percent stronger, all the hydrogen in the early universe would have fused into helium almost instantly. There would be no long-lived stars like our sun, no water, and no stable elements for planets or people. If it were slightly weaker, protons and neutrons could not bind together at all, and complex atoms would never form. The universe would be a featureless soup of hydrogen. The cosmological constant governing dark energy is tuned to an even more ridiculous precision. If it were a little larger, the universe would have expanded so rapidly after the Big Bang that galaxies and stars could never have coalesced. If it were a little smaller and negative, the cosmos would have collapsed back on itself long before life had a chance to arise. It is as if someone dialed in dozens of independent cosmic knobs to unimaginably precise settings, all to create a universe capable of hosting conscious observers. This staggering improbability is the fine-tuning problem. One powerful response to this puzzle is the anthropic principle. In its weak form, it is almost a tautology, but a profound one. It simply states that we must observe a universe compatible with our own existence. We could not possibly find ourselves in a universe that does not allow for carbon-based life, because we would not be here to ask the question. It is a selection effect, like a lottery winner marveling at their own luck, unaware of all the losing tickets. The weak anthropic principle does not explain why such a life-friendly universe exists, only that our observation of it is inevitable, given that we are here. The strong anthropic principle goes much further. It suggests the universe must have properties that allow life to develop at some stage. This version hints at a purpose or design, a universe that is compelled to produce observers. For many scientists, this feels like stepping outside of science into metaphysics. But there is a compelling, naturalistic explanation that emerges from the frontiers of cosmology, the multiverse. If our universe is just one bubble in an infinite, frothing foam of universes, each with its own random set of physical constants and laws, then the fine-tuning mystery evaporates. In an endless landscape of possibilities, every conceivable combination of constants will exist somewhere. We do not live in a miraculously tuned universe. We simply live in one of the rare bubbles where the numbers happen to fall right for stars, planets, and life. The vast, overwhelming majority of other universes would be stillborn, empty, or chaotic, devoid of any structure complex enough to wonder about its own existence. We are not lucky, we are inevitable, because in an infinite multiverse, every possible outcome must occur. Our particular bubble is not special, it is just ours. This idea transforms the question from why are the constants so perfect to why do we find ourselves in this particular bubble. The answer, again, is the anthropic principle. We could not find ourselves anywhere else. While the multiverse remains a theoretical framework, it offers a powerful escape from the need for a cosmic designer, grounding our improbable existence in a vast, perhaps infinite cosmic lottery. Yet it leaves us with a humbling perspective. Our entire reality, with all its beauty and complexity, might be just one accidental garden in an endless, mostly barren, multiversal desert. Our own galaxy, along with thousands of its neighbors, is not drifting aimlessly through the void. we are caught in a silent, relentless river, all flowing toward a mysterious destination. This is the 20th great cosmic question. What is the nature of the Great Attractor? For decades, astronomers have mapped the motions of galaxies, and they have uncovered a startling truth. Our entire local group, including the Milky Way and Andromeda, along with the entire Virgo supercluster of thousands of galaxies, is being pulled toward a specific point in the distant constellation Centaurus. This motion is superimposed on the general expansion of the universe, a peculiar velocity of over 600 kilometers per second toward something we cannot directly see. The source of this immense gravitational pull is what we call the Great Attractor. But why is it so mysterious? Its location lies directly behind the plane of our own Milky Way galaxy, in a region astronomers call the zone of avoidance. This is the thick band of stars, gas, and dust that makes up the galactic disk. It acts like a cosmic curtain, blocking our view in optical light. Trying to see the Great Attractor from Earth is like trying to spot a distant mountain range through a dense, blinding fog. For a long time, it was a gravitational phantom, a tug we could feel but whose source remained completely hidden. To pierce this veil, scientists had to turn to telescopes that see in wavelengths other than visible light. Infrared telescopes can peer through the dust, revealing the faint glow of stars. X-ray telescopes detect the superheated gas that fills the spaces between galaxies in massive clusters. By combining these views, we have begun to map the hidden landscape. What we have found is not a single, monstrous object, but an immense concentration of mass known as the Norma cluster, part of an even larger structure called the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is our true cosmic address, a filamentary web of hundreds of thousands of galaxies spanning over 500 million light-years. The Great Attractor appears to be the gravitational center of this vast supercluster. Yet, even this colossal concentration of galaxies may not fully account for the observed pull. Some scientists suspect the motion might be due to something even larger and more distant, an overarching flow toward an immense structure billions of light-years away, sometimes called the Shapley Attractor. The Great Attractor, then, might be just one milestone on a longer cosmic journey. This gravitational mystery teaches us a profound lesson about our place in the cosmos. We are not stationary observers. We are passengers on a galactic arc, swept along by currents of gravity generated by structures so vast they remained invisible to us for most of human history. The pull we feel is the signature of the universe's large-scale architecture, an architecture built from dark matter and woven into a web of stunning complexity. The search to understand the Great Attractor is a quest to map the hidden geography of our cosmic continent and to learn what immense forces are guiding our long-term fate through the dark. That immense pull toward the Great Attractor is a silent testament to gravity's absolute reign, a force that finds its ultimate expression in the black hole's perfect darkness. Yet even that darkness may not be eternal. Stephen Hawking made a prediction that shook the foundations of physics, a whisper from the void itself. He proposed that black holes are not completely black. Due to bizarre quantum effects at the very edge of the event horizon, they should emit a faint thermal glow, now known as Hawking radiation. This radiation causes black holes to slowly, over astronomical timescales, lose mass and evaporate. To understand this, you have to picture the quantum vacuum. Empty space is not truly empty, but a seething sea of virtual particle-antiparticle pairs constantly flickering in and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and paying the energy back. Now, imagine this happening right at the precipice of a black hole's event horizon. Occasionally, one of these virtual particles will fall in while its partner escapes into the universe. The escaping particle becomes real, carrying away a tiny amount of the black hole's energy. From the outside, it looks as if the black hole is glowing, radiating away its own mass, one quantum particle at a time. For a stellar mass black hole, this process is unimaginably slow, taking far longer than the current age of the universe. But for a tiny, primordial black hole, it could be happening now, potentially ending in a final, explosive flash of gamma rays. Hawking's calculation was a masterpiece, uniting quantum mechanics and gravity at the boundary of the known. But it created a paradox so severe it has divided physicists for half a century, the black hole information paradox. According to the pillars of quantum mechanics, information is never truly destroyed. It can be scrambled like the pages of a book burned to ash, but in principle, all the information about those pages is still encoded in the smoke and debris. If you throw that book into a black hole, the information about its contents, the words, the ink, the binding, is seemingly lost behind the event horizon. Hawking radiation, however, is thermal, random, and featureless. It carries no information about what fell in. So when the black hole finally evaporates completely, vanishing from the universe, what happens to the information locked inside? If it is truly lost forever, it violates a sacred law of quantum mechanics, the principle of unitarity, which says the evolution of the universe must be reversible in principle. Information cannot just vanish. This paradox suggests our understanding of either gravity, quantum mechanics, or both is fundamentally flawed at this extreme intersection. Resolving it is considered a critical stepping stone to a full theory of quantum gravity. In recent years, the fight to save information has led to astonishing new ideas. One is the concept of black holes having soft hair. This is not literal hair, but an elegant proposal that when matter falls into a black hole, it imprints an infinitely subtle, zero-energy pattern on the event horizon, like a gentle, permanent ripple. This soft hair could encode the information about what fell in, preserving it on the surface even as the black hole evaporates. The information would then be released in the final burst of radiation, scrambled but not destroyed. Another, more radical framework is the island conjecture, which emerges from the holographic principle. It suggests that as a black hole evaporates, a region in its interior, an island, becomes entangled with the radiation streaming out. The information about the infalling matter is not stored deep inside the singularity, but on this quantum-entangled island, which is, in a complex mathematical sense, also part of the outgoing radiation. It is as if the interior of the black hole reaches out and connects with its own future emissions to preserve the cosmic ledger. These are not just abstract games, they are desperate attempts to reconcile two pillars of reality. The fate of a single bit of information falling into a black hole may hold the key to understanding how space, time, and causality are woven together at the most fundamental level. The paradox forces us to choose: do we abandon a core tenet of quantum mechanics, or do we radically redefine what we mean by the inside of a black hole? The answer, when it comes, will illuminate the very nature of reality itself. The paradox of black hole information forces us to search for a framework where such conflicts cannot exist, a single, unified rulebook for reality itself. This brings us to the 22nd great cosmic question: is there a theory of everything? For centuries, the dream of physics has been to find one elegant set of principles that describes every force, every particle, and every interaction in the cosmos, from the quantum flutter of an atom to the majestic spin of a galaxy. Today, we have a spectacularly successful but incomplete map of the microscopic world, the standard model of particle physics. It is a triumph of human ingenuity, a collection of equations that catalogues all known fundamental particles and three of the four fundamental forces: the electromagnetic force, the strong nuclear force that binds atomic nuclei, and the weak nuclear force behind radioactive decay. Using the standard model, we can predict the outcome of particle collisions with breathtaking accuracy. It led to the discovery of the Higgs boson, the particle that gives others mass. Yet for all its power, the standard model is glaringly incomplete. It has no place for the fourth force, gravity. it cannot explain dark matter or dark energy. It treats the puzzling mass of neutrinos as an afterthought, simply plugging in measured values without explaining why they are so vanishingly small. The model is a masterpiece, but it is a masterpiece with holes, a partial map of a territory we know is far larger. The quest for a theory of everything is the attempt to draw the complete map. The most famous candidate is string theory. It proposes a radical shift. The fundamental ingredients of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. Just as different vibrations of a guitar string create different musical notes, the distinct vibrational patterns of these strings would give rise to every particle we see, from electrons to quarks to photons. Crucially, one specific vibration corresponds to the graviton, the hypothetical particle that would carry the force of gravity, seamlessly weaving it into the same tapestry as the other forces. To make the mathematics of string theory consistent, however, it demands extra spatial dimensions curled up into complex microscopic shapes. This leads to an even more ambitious framework, M-theory, which suggests that what we call strings might be just one slice of a richer, 11-dimensional reality where membranes and other objects exist. The promise is intoxicating, a single mathematical origin for all of existence. But this grand ambition faces a formidable and perhaps fatal criticism: testability. The energy scales at which strings vibrate and extra dimensions uncurl are a billion times beyond what our most powerful particle collider can reach. The theories make a vast landscape of possible predictions, but no clear, unique signature we can look for in an experiment today. They are, critics argue, beautiful mathematics but not yet science. This forces us to ask a deeper, almost philosophical question: is a theory of everything even possible? Or is our universe fundamentally a contingent, messy patchwork? Perhaps the laws we see are not the inevitable outcome of a single equation, but the frozen accidents of our cosmic history, the local bylaws of our particular bubble in a vast multiverse. In this view, searching for a single, elegant theory that explains every constant and force might be like searching for a single equation that explains every unique snowflake, a beautiful but futile hope. The dream of a final theory persists because it speaks to a fundamental human longing to see the universe not as a collection of unrelated parts, but as a coherent, comprehensible whole. Whether that wholeness is written in the vibrations of hidden strings, the geometry of a higher dimension, or is simply an illusion born from our limited perspective, remains the ultimate puzzle. The search itself compels us to look deeper, to ask if the complexity we see is the surface noise of a profound, underlying simplicity waiting to be heard. The quest for a theory of everything leads us to objects where the known laws are stretched to a screaming edge. Among the most terrifying and powerful things in the cosmos is a magnetar. Picture the corpse of a giant star, a core so dense that a single teaspoon of its material would weigh as much as a mountain. This is a neutron star, the remnant of a supernova explosion. Now take that neutron star and crank its magnetic field to an almost inconceivable level, a quadrillion times stronger than Earth's protective magnetic shield. That is a magnetar. Its magnetic grip is so intense that if one were located as far away as the moon, it could erase the data from every credit card on our planet. It is a cosmic magnet of pure, distilled fury. The power locked within this field is beyond human comprehension. It is stored energy, a tension in the very fabric of space-time around the star. And like any wound-up spring, it can suddenly release. The crust of a magnetar, a rigid shell of iron nuclei 10 billion times stronger than steel, is under constant, unimaginable stress from this magnetic prison. Occasionally, it cracks. These are starquakes, seismic events on a stellar scale. When the crust fractures, it unleashes a cataclysm. The magnetic field lines snap and reconnect, transferring that pent-up energy into a blast of radiation that can outshine our entire galaxy for a fraction of a second. We see these events as colossal gamma-ray flares, and they are thought to be the engine behind some of the most mysterious signals we detect, including many of those fleeting fast radio bursts. For a brief moment, a single city-sized object becomes the brightest thing in the gamma-ray sky. How does nature forge such a monstrous magnet? The leading theory points to the chaotic, hyper-fast birth of the neutron star itself. In the final moments of a supernova, as the stellar core collapses, a dynamo of unimaginable scale may ignite. The infant neutron star is spinning dozens of times per second, and its interior is a superfluid soup of neutrons and protons. This churning, conductive fluid, combined with the rapid rotation, could amplify a pre-existing stellar magnetic field to magnetar levels in a matter of seconds. It is a perfect storm of conditions, a cosmic generator that takes the dying breath of a star and turns it into a permanent magnetic scream. But the exact recipe remains uncertain, a puzzle locked inside the most violent explosion known to science. Studying magnetars is like conducting physics experiments under conditions we could never hope to create in a laboratory. They are natural laboratories for the behavior of matter under the most extreme pressures and magnetic fields possible. They allow us to test the limits of quantum electrodynamics, to understand how atoms themselves are deformed in such an environment, and to probe the strange state of matter in a neutron star's core. Each flare, each pulse, is a message from a realm where the rules are written in forces 1,000,000 billion times stronger than anything we know. By listening to these magnetic monsters, we are not just cataloging cosmic oddities, we are reading the signature of matter pushed to its absolute breaking point, teaching us what the universe is truly capable of when it decides to show its full, terrifying strength. The magnetic fury of a magnetar is a contained explosion, a focused blast of power, but the universe also flings individual particles with energies so monstrous they defy belief. These are ultra-high energy cosmic rays, atomic nuclei traveling at nearly the speed of light, each carrying the punch of a professionally thrown baseball, all compressed into a single subatomic speck. Their energy is staggering, millions of times greater than anything we can produce in our most powerful particle accelerators on Earth. They are the universe's natural cannons, firing bullets of pure energy across the void. Yet catching one is an event of incredible rarity. Only a few dozen of the very highest energy particles strike each square kilometer of our planet per century. They do not announce themselves with a flash of light we can see. Instead, when one of these galactic bullets slams into the upper atmosphere, it triggers a spectacular cascade. It smashes into an air molecule, creating a shower of secondary particles, which in turn collide and multiply, creating a vast, invisible avalanche of billions of particles raining down over an area the size of a small town. This is called an air shower. Giant observatories like the Pierre Auger Observatory in Argentina are built to catch these fleeting downpours. It is not a single telescope, but a sprawling array of over 1,600 water tanks spread across 3,000 square kilometers of prairie, an area larger than Rhode Island. When particles from an air shower zip through the pure water in these tanks, they create a faint blue flash of light which sensitive detectors record. By timing when the wave of particles hits different tanks, scientists can reconstruct the direction of the original cosmic ray and estimate its colossal energy. But here lies the profound puzzle, a cosmic roadblock called the Greisen-Zatzepin-Kuzmin, or GZK cutoff. The universe is not empty. It is filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation, a sea of low-energy photons bathing all of space. For an ultra-high energy proton or atomic nucleus traveling across intergalactic distances, this background is not a gentle mist, it is a thick fog. As the particle races along, it should constantly bump into these microwave photons. Each collision saps a little of its energy, like a high-speed runner constantly tripping over tiny pebbles. Over distances of a few 100 million light-years, this process should drain these particles of their ultra-high energy. They should be slowed down, their extraordinary punch reduced to a mundane level, and yet we keep detecting them. This means these cosmic cannonballs cannot have come from too far away. They must originate within our local cosmic neighborhood, within a sphere of roughly 300 million light-years. So what nearby cosmic engine is powerful enough to accelerate a single particle to such an insane velocity? The suspects are few, and each is a titan. The prime candidate is the active galactic nucleus, the supermassive black hole at the heart of a galaxy, feeding on vast amounts of gas and dust. The chaotic, magnetized maelstrom around such a black hole could act as a natural particle accelerator of unimaginable scale, flinging matter outward in jets that stretch for thousands of light-years. Another possibility is the aftermath of a gamma-ray burst, the death cry of a massive star collapsing into a black hole, which could produce a shockwave capable of imparting tremendous energy to surrounding matter. But when scientists point their instruments back along the incoming paths of these ultra-high energy cosmic rays, the results are frustratingly murky. The trajectories are bent by the magnetic fields that permeate interstellar and intergalactic space, making it incredibly difficult to trace a straight line back to a single, glaring source on the sky. It is like trying to find the origin of a leaf blown into your yard during a hurricane. The path is twisted and lost. The Auger Observatory has found some tantalizing correlations, hints that the highest energy rays might be coming from the general direction of nearby galaxies with active supermassive black holes. But it is not a smoking gun. The mystery endures, pointing to a terrifying possibility. Perhaps we have not yet identified the true source. Could there be something even more violent and exotic in our cosmic backyard? A phenomenon we have not yet imagined, capable of focusing the energy of a star into a single atomic projectile. Each rare flash in a water tank in the Argentine desert is a message from one of the universe's most powerful and secretive accelerators, and we are only just beginning to decode its return address. Those cosmic cannonballs push the limits of known physics, but sometimes the most revealing mysteries are found in the smallest, quietest discrepancies. For decades, two silent explorers, the Pioneer 10 and Pioneer 11 spacecraft, presented scientists with a ghost in the machine. After completing their historic missions to Jupiter and Saturn, these twin probes continued their endless journey into the dark, becoming humanity's first emissaries to leave the solar system. But as they drifted farther and farther from the sun, tracking their precise positions revealed something bizarre. Both spacecraft were slowing down ever so slightly more than they should have been. The sun's gravity was pulling them back, of course, but there was an extra, tiny deceleration. A constant sunward tug equivalent to just 10 billionths of the gravity you feel standing on Earth. It was as if a faint, invisible hand was gently applying the brakes. This was the Pioneer anomaly. For years, this minuscule drift haunted physicists. It was a whisper of a problem, a data point that stubbornly refused to fit. Could it be a sign of new physics, perhaps a flaw in our understanding of gravity itself over vast distances, a hint of modified Newtonian dynamics, or MUND, which some propose to explain galaxy rotation without dark matter? Maybe it was evidence of unseen dark matter clumped in our solar system, or some other cosmic secret. The anomaly became a classic scientific detective story, a puzzle box that took nearly 30 years to fully pry open. The breakthrough did not come from rewriting the laws of the cosmos, but from an astonishingly meticulous piece of engineering archaeology. The key suspect was not a new force, but the spacecraft themselves. Pioneer was powered by the decay of plutonium in its radioisotope thermoelectric generators. This process created heat, which the spacecraft needed to radiate away into space to avoid overheating. Scientists realized that this thermal radiation did not escape perfectly evenly in all directions. more heat was emitted from the back of the spacecraft, from the warm electronics compartments facing away from the sun than from the front. This created a tiny but constant recoil force, like the faint push you feel from warm air leaving a heater. Photons of infrared light carrying momentum were acting as a microscopic photon rocket, gently pushing the craft backward toward the sun. Proving this was a monumental task. The original engineers who built Pioneer had long since retired. The team had to track down old blueprints, thermal models, and even reconstruct the power output of the decaying plutonium cores over decades. They built a stunningly detailed computer model of the entire spacecraft, accounting for every bolt, every instrument, and how heat flowed and radiated from every surface. When they finally ran the simulation, the numbers aligned almost perfectly. The thermal recoil from the spacecraft's own waste heat explained the anomaly. The ghost was not a new law of physics, but the consequence of an old one, thermal radiation pressure, acting in a complex, real-world system. The resolution of the Pioneer anomaly stands as a triumph of careful, persistent science. It is a case study in humility and rigor, showing that before we invoke revolutionary new physics, we must exhaust every mundane explanation, no matter how painstaking the search. Yet its legacy is dual-edged. It reminds us that such tiny, persistent anomalies are the universe's way of asking us to look closer. While this one led back to the spacecraft's own plumbing, the next one might not. The search for truth often begins with a faint, unexplained signal in the data, a whisper that either fades into the hum of known mechanics or grows into a roar that changes everything. That meticulous search for truth in the faintest data leads us to a night when the signal was anything but faint. On August 15, 1977, a radio telescope at Ohio State University known as the Big Ear was performing its routine, automated scan of the sky, listening for whispers from the cosmos. The next day, a volunteer named Jerry Amon was sifting through the reams of printed data, a long scroll of letters and numbers representing signal strength. His eyes locked onto a sequence, 6 characters that stood out with shocking clarity. He circled them in red pen and in the margin wrote a single, emphatic word: wow. The sequence, 6EQUJ5, was a code. It meant the telescope had detected a narrowband radio signal at the frequency of 1,420 MHz, a frequency that happens to be in a protected band where earthly transmitters are forbidden, a quiet channel in the cosmic radio. It was 72 seconds of pure, powerful tone, exactly the kind of signal scientists had predicted an advanced civilization might use as a beacon. It rose to peak intensity and then faded away as the Earth's rotation carried the telescope's gaze past its source, a perfect curve matching the expected profile of a celestial source. It came from the direction of the constellation Sagittarius, near a star group called Chi Sagittarii, and then it was gone. Despite decades of dedicated searches pointed at that same patch of sky, the signal has never been heard again. It remains a singular event, the strongest, most compelling candidate in the history of the search for extraterrestrial intelligence. The characteristics were perfect, too perfect for mere cosmic static. Natural astrophysical events like pulsars or stellar flares produce broadband noise, a hiss across many frequencies. The wow signal was a pure, narrow tone, a cosmic whistle. So what could have caused it if not intelligence? Over the years, scientists have proposed several natural explanations, but each struggles to fit all the facts. One intriguing idea involved comets. In 2017, it was suggested that the signal could have been a reflection of earthly radio noise off the hydrogen cloud surrounding a passing comet. The timing and location were checked against known comets in the area at the time, but none were found to be present. The hypothesis, while creative, left more questions than answers. Another possibility is that it was a signal from a human satellite or spacecraft, a piece of space junk briefly reflecting a transmission. Yet the frequency was protected, and no known satellite matched the signal's precise profile and duration. The most likely natural culprit, a passing asteroid or other solar system object, fails because such objects do not emit strong, narrowband radio waves. The signal's intensity was also remarkable. The Big Ear telescope used 2 feed horns slightly offset to scan the sky. A genuine celestial signal should appear in one horn, disappear for a moment, and then appear in the second horn as the Earth turns. The WOW signal was detected in only one of the 2 horns. This oddity could point to a transient source that winked out between scans, or it could be a clue that the signal was not celestial at all, but something much closer, perhaps even terrestrial interference that by pure, staggering chance mimicked the signature of an extraterrestrial beacon. That is the maddening heart of the mystery. It was a signal that matched our best predictions for what we should look for, appearing in the quietest part of the radio spectrum, but it left no repeatable evidence, no way to verify its origin. In science, reproducibility is everything. A single, unrepeatable event, no matter how tantalizing, remains an anecdote, a ghost in the data. The WOW signal is the ultimate cosmic tease. It stands as a monument to both the promise and the profound frustration of SETI. It tells us that if there are others out there, they are either silent, speaking on channels we do not yet understand, or their messages are fleeting bursts we have only just begun to catch. We are left with a circled notation on a faded printout, a 72-second sigh from the depths of space that asked a question we have spent half a century trying to answer. That single, unrepeatable whisper from the cosmos stands in stark contrast to a bias written into the very fabric of our existence. The WOW signal is a question mark, but the dominance of matter over antimatter is a definitive existential fact. We are the children of that 1 in 10 billion anomaly, the leftover ash from a near-perfect annihilation, but merely stating the problem is not enough. To understand how our universe chose substance over light, we must meet the 3 strict criteria laid out by the physicist Andrei Sakharov. These are the non-negotiable ingredients for creating a matter-dominated cosmos from a symmetric beginning. First, there must be a process that treats matter and antimatter differently, a violation of charge parity symmetry or CP violation. Think of it as a cosmic seesaw that tips slightly heavier on the matter side. Second, the universe must have been out of thermal equilibrium. It cannot be a static, simmering pot. It must be a dynamic, cooling system where reactions can run one way and not easily reversed. And third, the interactions must not conserve baryon number. This is the most technical condition, but it is crucial. It means the processes must be able to change the net number of matter particles in the universe, creating more quarks than antiquarks from the energy of the early fireball. Our current standard model of particle physics possesses all 3 of these conditions, but in a tragically feeble way. We have observed CP violation in the decays of exotic particles like kaons and B mesons in our colliders. The universe was certainly out of equilibrium as it expanded and cooled from the Big Bang. And there are hypothetical processes within the standard model, like electroweak baryogenesis, that could, in principle, produce a baryon asymmetry. Yet when physicists run the numbers, the result is a devastating shortfall. The amount of CP violation we have measured is billions of times too small to account for the overwhelming sea of matter we see around us. It is as if we found a single drop of water and tried to claim it created the Pacific Ocean. The standard model's engine is not powerful enough to drive the creation of our entire reality. This forces us to look beyond, to new physics operating at energies we can only dream of recreating. One of the most compelling ideas is leptogenesis. This elegant theory ties the fate of matter to the ghostliest particles we know, neutrinos. It begins with the existence of super-heavy, right-handed neutrinos, particles predicted by many extensions of the standard model. In the searing heat of the very early universe, these heavy neutrinos would have decayed. Through CP violating processes, they would have decayed slightly more often into normal matter particles than antimatter particles. This tiny bias would have generated an excess of ordinary leptons like electrons and neutrinos. Then, through a cascade of subtle interactions known as Sphaleron processes, this lepton asymmetry would have been converted into the baryon asymmetry we see today, the excess of protons and neutrons that built our world. In this view, the faint neutrinos streaming through your body right now are the distant relatives of the process that made your existence possible. Another pathway is electroweak baryogenesis, which focuses on a pivotal moment in cosmic history. As the universe cooled through a critical temperature, the Higgs field, which gives particles their mass, underwent a phase transition. Think of it like water freezing into ice. If this transition was sudden and violent, creating bubbles of the new phase that expanded and collided, it could have created conditions of extreme non-equilibrium. Within the walls of these colliding bubbles, CP-violating interactions could have efficiently produced an excess of quarks over antiquarks, locking in the matter dominance as the new phase took over. The challenge is that in the standard model, this electroweak phase transition is not violent enough. It is a smooth crossover, not a sharp break. But many theories beyond the standard model, like supersymmetry, predict new particles that could make the transition sudden and dramatic, turning this idea into a viable cosmic engine. The hunt for the true source of our existence is now a multi-pronged experimental crusade. Next-generation neutrino experiments like DUNE in the United States and HyperCamioc and in Japan will study neutrino oscillations with unprecedented precision. They are searching for a specific form of CP violation in the neutrino sector itself. Finding it would not only prove that neutrinos and antineutrinos behave differently, but would also provide a critical piece of the puzzle for leptogenesis models. Meanwhile, at the energy frontier, the Large Hadron Collider and its planned upgrades are scouring for any sign of new particles or interactions that could have made the electroweak phase transition more violent. They are looking for the fingerprints of physics that operated at trillion-degree temperatures in the universe's first fleeting moments. This is not an abstract pursuit. It is a forensic investigation into our own origin story. Every galaxy, every star, every atom in your hand is evidence from a crime scene 13.8 billion years old. The culprit is a set of physical laws that favored matter just enough to leave a universe behind. We are now reconstructing those laws, searching for the precise mechanism that tilted the cosmic scales and allowed something rather than nothing to endure. The answer will tell us whether we live in a universe where our existence is a fragile, statistical fluke, or the inevitable outcome of a hidden asymmetry woven deep into the laws of nature. That delicate asymmetry, the 1 in 10 billion miracle that gave us a universe of matter, laid the groundwork for the most magnificent architecture imaginable. Zoom out from any single galaxy past clusters and superclusters, and the true pattern of the cosmos reveals itself. The universe is not a random scattering of islands, but a vast, intricate web. Galaxies are strung along luminous filaments like dew on a spider's silk, surrounding immense, dark voids that stretch for hundreds of millions of light years. This is the cosmic web, the largest single structure in all of nature. It is the skeleton of the observable universe, and its origin story is written in the faintest whispers from the beginning of time. Those first seeds were planted in the inflationary epoch, a fraction of a second after the Big Bang. Quantum fluctuations, tiny ripples in the fabric of space-time, were stretched to cosmic proportions by that period of hyper-fast expansion. These ripples became slight variations in density, places where there was just a little more matter than average. After the universe cooled and neutral atoms formed, gravity went to work. Over billions of years, it acted as a cosmic amplifier. Regions with a slight overdensity pulled in more material from their surroundings, growing denser and denser. Meanwhile, the underdense regions were drained, becoming emptier and emptier. Think of it like water draining from a landscape. The water flows into the valleys and gullies, carving them deeper and leaving the high ground isolated. In the cosmos, dark matter acted as the gravitational scaffold. It collapsed first into halos, invisible spheres of mass that then attracted ordinary gas. The gas cooled, condensed, and ignited into the first stars, lighting up the galaxies we see today. These galaxies did not form in isolation. They were born along the intersections and strands of this dark matter framework, tracing out the web. Mapping this colossal structure is one of astronomy's grandest cartographic projects. For decades, surveys like the Sloan Digital Sky Survey have painstakingly measured the positions and distances of millions of galaxies. By plotting them in 3 dimensions, the ghostly outline of the web emerges from the data, a statistical confirmation of a pattern predicted by theory. The next generation of missions, like the European Space Agency's Euclid telescope, will take this map to a new level. Euclid will observe billions of galaxies, charting the web's structure over 10 billion years of cosmic history. It will use a phenomenon called weak gravitational lensing, where the light from distant galaxies is subtly warped by the dark matter filaments in the foreground to trace the invisible scaffolding directly. But for all its grandeur, the cosmic web holds deep mysteries. The precise properties of the dark matter halos that host galaxies are not fully understood. What is their internal structure? How do they merge and grow over time? Even more complex are the feedback processes that shape the visible web. Galaxies are not passive passengers. Supernova explosions and violent jets from supermassive black holes pump enormous energy back into their surroundings. This feedback can heat gas, prevent it from cooling to form new stars, and even blow it out of galaxies entirely, redistributing matter along the filaments and into the void. It is a dynamic, self-regulating system where the life cycles of stars and black holes sculpt the very large-scale structure they inhabit. The cosmic web, therefore, is not a static fossil. It is a living, evolving network, a record of gravitational growth written in dark matter and illuminated by the violent, brilliant lives of galaxies. To understand its full story is to read the autobiography of the universe, from its quantum infancy to the glittering, filamentary present. The cosmic web is a testament to the enduring power of gravity, a force governed by numbers we consider sacred and unchanging. But what if the universe's rulebook itself is not written in permanent ink? Question 29 asks a question so fundamental it threatens to unseat all of physics. Can the laws of physics change over time or space? We have built our entire understanding of the cosmos on a bedrock assumption that the fundamental constants and laws are the same everywhere and for all time. The speed of light in a vacuum is always the same, the strength of gravity does not waver, and the charge of an electron is identical here in a distant galaxy and 10 billion years in the past. This principle of constancy is the foundation of cosmology. It lets us trust that the light from a quasar billions of light years away is governed by the same physics as the light in our laboratories. But a handful of daring observations have suggested this foundation might have a tiny, terrifying crack. The suspect is a seemingly obscure number called the fine structure constant, often denoted by the Greek letter alpha. It is not obscure at all. It is a magical combination of 3 more fundamental constants: the charge of the electron, the speed of light, and Planck's constant. This pure, dimensionless number, approximately 1 over 137, governs the strength of the electromagnetic force. It controls how tightly electrons bind to atomic nuclei, the colors of light atoms absorb and emit, and the very stability of matter itself. In the late 1990s, a team of astronomers led by John Webb began analyzing the light from incredibly distant quasars. These brilliant beacons are the cores of ancient galaxies, and their light passes through clouds of interstellar gas on its multi-billion-year journey to Earth. Atoms in those clouds absorb specific, precise wavelengths of the quasar's light, leaving dark lines in its spectrum like a cosmic barcode. The exact positions of these absorption lines depend on the value of the fine structure constant in those clouds when the light passed through them billions of years ago. When Webb's team painstakingly measured these lines, they found a faint but persistent signal. The lines were not exactly where our current local value of alpha would predict. They were slightly shifted. The interpretation was staggering. It suggested that billions of years ago, in certain directions of the sky, the fine structure constant was minutely smaller than it is today. The electromagnetic force was ever so slightly weaker. The change is minuscule, only a few parts in a million over 10 billion years, but if real, its implications are revolutionary. A varying constant would shatter Einstein's equivalence principle, a cornerstone of general relativity which assumes the constancy of physics. It would imply that the vacuum of space itself has properties that evolve, and it could be a direct signature of extra dimensions. In some string theory models, the extra, curled-up dimensions are not static. They could slowly expand or contract over cosmic time. Since the strengths of the fundamental forces are determined by the geometry of these hidden dimensions, their evolution would cause constants like alpha to drift. We would be witnessing the slow breathing of the cosmos's hidden geometry. The physics community reacted with intense skepticism, as it should. Extraordinary claims require extraordinary evidence. The measurements are at the very edge of precision, and systematic errors are a huge concern. Could the effect be due to unknown chemical compositions in the distant gas clouds or subtle instrumental biases? Other teams have performed their own analyses, some supporting a variation, others finding no change at all. The debate is fierce and ongoing. To settle it, scientists are mounting a two-front war. In space, powerful new instruments like the espresso spectrograph on the Very Large Telescope are re-observing those ancient quasars with unprecedented accuracy, hunting for any systematic error that could mimic the signal. On Earth, ultra-precise laboratory experiments are testing the constancy of constants in the here and now. Atomic clocks, the most precise timekeeping devices ever built, compare the tick rates of different types of atoms. Their rhythms depend on different fundamental constants. By monitoring these clocks over years, scientists can see if the constants are drifting relative to each other, even by a minuscule amount over a human lifetime. So far, the laboratory tests have found no evidence of change. The universe's local rulebook appears rock solid, yet the astronomical whisper persists, a ghost in the data that refuses to be fully dismissed. We are left in a profound state of uncertainty. Are the laws of physics the eternal, universal bedrock of reality, or are they more like local bylaws, slowly evolving in a cosmos far stranger than we dreamed? The answer will determine whether we live in a universe with fixed rules, or one that is still writing its own laws as it expands and ages. The possibility of changing laws brings us back to a paradox where two sets of laws, gravity and quantum mechanics, collide with absolute fury. The black hole information paradox is not a minor puzzle, it is a fundamental crisis. We left it with a stark choice. Either information is truly lost when a black hole evaporates, violating quantum mechanics, or something dramatic must happen at the event horizon to preserve it. This dilemma gave birth to one of the most unsettling ideas in modern physics, the firewall. Imagine an astronaut driven by unimaginable courage, deciding to cross the event horizon of a large, quiet black hole. According to Einstein's general relativity, this should be a smooth, if one-way, journey. The astronaut would feel no sudden jolt, no dramatic barrier, just the inexorable pull of gravity as they cross the point of no return. The principle of equivalence, a cornerstone of relativity, assures us that free fall feels like floating in empty space. But if quantum mechanics is to be saved, if information is to be preserved, this gentle passage may be a fantasy. To prevent information from being lost inside, some theories suggest the event horizon must be a place of violent transformation. The infalling astronaut would not experience empty space. Instead, they would encounter a searing wall of high-energy particles, a literal firewall of unimaginable temperature that would incinerate them and everything they carried into its fundamental bits long before they reached the interior. The information in their body would not fall in. It would be scrambled and encoded onto this energetic boundary, later to be released in the Hawking radiation. The firewall saves information, but at a terrible cost. It blatantly violates Einstein's prediction of a smooth spacetime at the horizon. We are left with two mutually exclusive realities, both demanded by our best theories. Either the universe allows for a gentle passage into a black hole and sacrifices the sanctity of quantum information, or it erects a lethal wall to protect information and shatters our understanding of gravity. This is the firewall paradox, and it screams that our understanding of reality is incomplete. To resolve it, physicists have been forced to rethink the nature of space, information, and reality itself. The most promising path forward is the holographic principle, a concept so radical it redefines where information truly resides. It suggests that all the information needed to describe everything within a volume of space, including our three-dimensional universe, can be perfectly encoded on its two-dimensional boundary, like a cosmic hologram. For a black hole, this means the information of everything that falls in is not lost in the mysterious singularity. It is painted in exquisitely scrambled form on the event horizon itself. The three-dimensional interior we imagine is a kind of illusion, a projection from that two-dimensional data. This idea finds a powerful mathematical expression in something called the ADS/CFT correspondence, a precise duality that shows a gravitational theory in a certain type of space is equivalent to a quantum field theory on its boundary. In this framework, the black hole information paradox in the gravitational description translates to a solvable problem about information scrambling in the quantum description. The paradox dissolves because the information never actually falls into a place where it can be lost. It just gets terribly mixed up on the surface. But how does this abstract principle translate to a practical rescue of information? The answer may lie in the architecture of quantum computers through a concept called quantum error correction. In a quantum computer, information is stored in fragile quantum states. To protect it from noise and decoherence, scientists spread the information out across many entangled physical qubits. Even if you damage some of the qubits, the original information is not lost. It can be recovered from the correlations among the surviving ones. The holographic universe may work the same way. The information about a star that fell into a black hole is not stored in one place on the horizon. It is spread out or delocalized across the entire surface in a highly entangled network. An observer falling in with the star would not see this information, just as you cannot read a single sentence from a book that has been pulped and mixed into a vat of other books. The information is there, but it is globally encoded. Hawking radiation, then, is not random thermal noise. It is the slow and complex process of this entangled horizon decoding itself, releasing the scrambled information back into the universe as the black hole evaporates. The firewall, in this view, may be an artifact of asking the wrong question from the wrong perspective. From the viewpoint of an outside observer who never falls in, the information remains on the horizon. From the viewpoint of someone who chooses to fall, the rules of quantum entanglement might allow for a smooth passage, with the information effectively teleported out via the intricate web of correlations. The infalling observer and the information become so deeply entangled with the Hawking radiation that no single description is complete without the other. This puzzle, the clash over a single bit of information at a black hole's edge, is not an academic sideshow. It sits at the very heart of the quest to unify physics. To solve it is to understand how space-time itself emerges from something more fundamental, likely a vast network of quantum entanglement. The black hole is the universe's ultimate laboratory, forcing us to choose between cherished principles and guiding us toward a deeper truth, that the dimensions we experience, the forces we feel, and the information that defines reality may all be different faces of a single, astonishingly interconnected system. The silence from the event horizon is not empty, it is the sound of our current theories breaking and of a new understanding struggling to be born. We have journeyed to the very edge of understanding, from the ghostly grip of dark matter to the silent scream of the wow signal. 30 questions, each a doorway into a deeper layer of cosmic mystery. They remind us that our universe is not a solved puzzle, but a living conversation, a story still being written. Every one of these profound unknowns, from the fine-tuning of the constants to the paradox inside a black hole, is not a failure of science, but its very purpose. They are the blank spaces on the map that call us to explore, the whispers that pull us toward a greater truth. These mysteries define our place in the cosmos. We are the part of the universe that has become conscious of itself, capable of looking up at the stars and asking, why? The fact that we can pose these questions, that we have built telescopes to peer back to the dawn of time and colliders to recreate its first moments, is a triumph in itself. Our quest is far from over. Right now, telescopes like Euclid are mapping the dark web of the cosmos, while deep underground, detectors wait for the faint tick of a dark matter particle. In laboratories, atomic clocks monitor the constancy of physics itself, and radio telescopes silently scan the sky, listening for another whisper. This is our shared human adventure, the collective project of a species striving to comprehend its home. So keep looking up. Let the unanswered questions not frustrate you, but inspire you. Let them fill you with wonder at the sheer scale of what we do not yet know. The universe is not hiding its secrets out of spite, but inviting us to look closer, to think deeper, to imagine more boldly. The next great discovery could be announced tomorrow. Which of these cosmic mysteries keeps you awake at night? Is it the haunting silence of Fermi's paradox, the terrifying precision of the fine-tuning, or the mind-bending nature of consciousness itself? Share your favorite unanswered question in the comments below, and let's continue the conversation. If you want to join us on this ongoing voyage to the edges of reality, be sure to subscribe. Our exploration of the final frontier has only